Okay, so if you call it, what do you call a solution that has something dissolved in it, like sugar and water or salt water?
Aqueous.
Aqueous, okay? But there's another word we used back in Unit 1. All right, for example, if you have sand in water, sand does not dissolve in water. What do you call that? Heterogeneous. What do we call something that does dissolve in water besides aqueous? Homogeneous. This whole unit is about the aqueous / homogeneous solutions. We're not talking about heterogeneous at all. So some definitions to actually talk about. This goes back to Unit 1, but there is some new definitions we've got to cover. So what we're doing is building upon what we talked about way back when. Solution, basically, when I say the word solution, I'm not talking about a solution to your problems. A solution is what we use in chemistry as something that is dissolved. Okay, so for example, I'm going to bring this up. A lot of y'all drink coffee or tea, sweet tea or coffee, or neither. Okay, well anyway, I hope not. Kool-Aid? Okay, because Kool-Aid falls in this too. But anyway, whenever you put sugar or cream or something in the coffee or tea or whatever, do you see the sugar? Yeah. Well, probably at the beginning, but after you stir it a bit, then you end up losing it. So a solution, when I say the word solution, we're talking about the homogeneous automatically, the ones that do dissolve, okay? They say a mixture of two or more substances in a single physical state. Now, here's the thing. You're only going to be responsible for only two things, not more, okay? We could dissolve more in a solution, but only think of like water and sugar or something like that, okay? Water and salt. Try to think of only two things at a time. Don't try to think of more than two in this unit, okay? Because we're only going to do two. There's a lab that goes along with it. I call it the Kool-Aid lab because obviously you're making solutions of Kool-Aid. And what you're going to do is, I'll give you the overview of it. Basically, you make different concentrations like we did in chemistry, but you're actually going to get to drink these. And you got to tell me if it's sweet or not sweet, and do you like it, do you not, and all that kind of stuff. A solute, you do need to know these two definitions. This is a solution which is composed of two parts, the solute and the solvent. That's why I say only think of two things like salt and water. Yeah. Solute is the thing that's being dissolved. The solvent is the stuff doing the dissolving. Okay? People get these two mixed up. Yeah. But notice I use the word solute and I pronunciate it, and solvent, because that helps break down like you knowing the difference between the two. So if I said salt water, okay, what is salt? Is it the solute or solvent? Solute. Solute, yeah. If it's salt, because it's being dissolved. If I say water, you say solvent. Solvent. It's the stuff doing the dissolving. Most of the time, it's going to be the liquid. Now, I'll go ahead and tell you, the universal solvent is the thing that is composed of most of the earth, which is water, or the surface of the earth. We don't know most of the earth. Anyway, so that's what you need to think about. It dissolves everything. That's why we like water so much, and water has a lot of properties that we're going to end up talking about in here. So if I say sugar and water, okay, sugar would be your solute, and water would be your solvent. That's the two things we got to talk about. So this is not in your slide, but I'm going to write this on the board as soon as I find my markers. Okay, here we go. All right. Oh, no. So when you take a solute and you add it to a solvent, guess what you get? A solution.
Kool-Aid.
So a solution is not one of these. It's both at the same time.
So it's the solution of the problem, it's the solution.
Kool-Aid, water. Sugar, coffee. So a substance that dissolves in another substance is said to be soluble. This is a definition you already know. A substance that is not to be dissolved is said to be insoluble. However, we didn't talk about these two yet. All right, two liquids, okay? If they do dissolve in each other, they are miscible, okay? You don't say miscible. I'm sorry, no, you don't say mixable. You say miscible. I said it backwards. Some people want to say mixable. No, it's miscible. That's how you spell it. Mixable is not a word. I know. I thought it was too. Yeah. Anyway, so like when you put cream in your coffee, that is two liquids dissolving each other. Or not dissolving each other, one's dissolving the other. However, not all liquids dissolve each other. For example, oil and water. Nope. Do they mix? Nope. Nope. No matter how much you try. And we're going to talk about why they don't mix. There is some chemistry behind it. Yeah, that's actually it. That's it. It's polarity.
That's why.
I think I told y'all. All right. One reason why, and we'll talk about why things do mix, if they're both polar, they dissolve each other. If they're both nonpolar, they dissolve each other. But polar cannot dissolve nonpolar, and nonpolar cannot dissolve polar. There is a two separate deal there. For example, two oils can dissolve each other because they're both nonpolar. So anyway, 4 definitions there. You know the first 2 already. The next 2 were terms that you got to know. Obviously, these make good, true, and false questions. Okay, so the solute is a part of the solution that is being dissolved, usually the lesser amount. That is a good thing to write down right there. So we are going to deal with mass and volume. If it's smaller, it's usually stuff that is going to end up being dissolved. Okay, you can't dissolve 800 pounds of sugar in 2 milliliters of water. It doesn't work that way. In fact, the water wouldn't even dissolve anything. You got to have more liquid than you are going to have the solid, and that's mostly what you're going to see in this unit. We're just going to assume that's the main thing, but we can have many combinations of not just liquid and liquid and solid and liquid. We can have gas on gas, gas on liquid, liquid on liquid, solid on liquid, gas on solid, liquid on solid, solid solid. I mean, it's many different examples we could do here. But anyway, all right, so concentration basically is the ratio. And when you hear the word concentrate, please don't just stare at your test. But concentrate has to deal with the amount of solute per solvent. Well, here we go, that word per again. In other words, it's like miles per hour. That's a division. That's a ratio. So we're going back to ratios again. Basically, it's the ratio between solute and solvent. I'm just saying the words. So down here at the bottom it says concentration is essentially a ratio of solute to solvent. Anyway. So concentration. All right, so here are the list of the ones you're going to have to know. There are 4. The most common, the 90% of the time, and this is the main one I care about, is molarity. If you understand molarity, you can approach college chemistry with a pretty good mind. It happens. But anyway, so these are the 4. There is molarity, there is molality, which we'll talk about molality later. They sound exactly alike. The only difference is different units. Mole fraction and percent by mass. Believe it or not, percent by mass is really easy. It's part over whole times 100. So there's one you already know. It's part of your solute divided by your whole, which is the whole mass of the whole thing.
No.
Yeah. So all those percent problems do come into play. Mole fraction is kind of silly, but we still have to do it out there. All right, so we're going to talk about each one of these guys. Molarity is the one we're going to spend the most time on today. So here's your formula. So formula number 1 is molarity. We used capital M. If you want to know why in the last unit we don't use an M for molarity, let me jump back a second. Here's the reason why. M was already taken by molality. Okay? And capital M was already taken by molarity. So that's why we use the letter N. It was already taken. And plus amount sounds a little bit cooler for N. I don't know. What are you going to do? All right, so anyway, moles of solute over liters of solution. Now, let's keep this in mind. I'm going to leave this up here so you can kind of get an idea of what we're talking about. So the units we're going to use for the solute is going to be moles. So can you measure out moles directly in lab?
Yeah.
No.
No.
You can't. But you can measure out what?
Mass.
Mass. Can you convert that mass to moles?
Yep.
That's what you're going to have to do. So you're doing that same stuff. You already know how to do that. Then you got to put it over liters of solution. Now keep this in mind. That's not solvent. Look very closely. Moles of solute over liters of solution. What is solution? It is a volume. Liters is, but what is solution?
That's what you get when you combine the solute and the solvent.
Guess what all of these formulas are?
Ratio.
They're all part over whole. Except one. One of them is not. And there's only one that is not. But if you keep in mind they're all part over whole, you'll memorize the formulas. People overthink it. Okay, so anyway. So I'm going to shorten down this formula here. Molarity is equal to moles of solute over liters of solution. Can you divide? So in other words, if you put the top guy in moles, the bottom guy in liters, you divide. And there's your concentration. That's the ratio. Guess what? The higher the concentration, the higher this number is, the higher this number is going to be, which tells you how much more concentrated it is. And that makes sense. Okay? If you add more sugar into water and drink it, it's going to taste what?
Sweeter.
A lot sweeter.
Lot.
A lot. Okay? You put a lot of salt in the water. Guess what it's going to taste like?
Salty.
Very salty. Yes. Salty must save me for myself. All right. Now here comes the big question. What do you use for units? Well, do you remember density?
No.
What's the units for density?
We're looking at grams.
There is a gram involved.
Gram part slash mole.
That is molar mass, which is a ratio. Okay, so you're not wrong there, but that is another
Gram
one.
over millimeter, oh God, something like that. Millimeters.
Grams over
Something
Cubic meter.
cubic centimeters, or grams over milliliters, right?
Right.
So we also said molar mass was grams per mole, and then you also said grams per centimeter cubed for density. So these two are for density. This is molar mass. Guess what? The unit for molarity is moles over liters. Moles per liter. There's no special thing for it. So here's the thing. You can either use mole per liter for your units or the capital M. Doesn't matter. They're both the same thing. Okay? All right. So I'm just telling you that's a ratio. So you're going to have ratio units. Okay? Okay. We say the word molar. Okay? We're not talking about the mole in the back of your mouth. We're talking about molar. So I say this is your molar concentration. All right? This is a molar solution, which means concentration. Okay? Does everybody understand what concentration means?
Yep.
Okay? So, all right. 2 moles for every liter of solution. All right? So if there are 3 liters of this solution, how many moles are there going to be? All right? So, yeah, they're going to be 3 moles. So if I have a 2 molar solution, all right, and I have 3 liters of this solution, how many moles do I have then?
6.
You have 6. Okay? Why? Well, you just did it. You don't know you did it, but you did it just like you would as a ratio.
Yeah.
If I have 3 liters, how many moles do I have?
6.
6.
Back down.
This, because let's think about it. You cross multiply, x is going to equal 6. All right, so what is the molarity of a solution of NaOH if 10 grams of NaOH, okay, list everything out, by the way. It wouldn't hurt, okay? So they give you 10 grams of NaOH dissolved in enough water to make 225 milliliters of solution. All right, so here's the thing. You could try dividing that, but that's not going to be moles per liter, is it? No, that'll be grams per milliliter, and that really is not really density because this is not the same thing as that. They're not the same, like this is NaOH, that's water and NaOH. So you can't really do that. But we're doing concentration. And remember what concentration is moles per liter. So there's 2 things you got to do here. You need to put this guy in moles, and then you need to put this guy in liters before you plug it in. So I'm going to do it the way y'all are more familiar with, rather than my way. My way is that whole crisscross thing, but doing it all at once, but we're not going to do that. All right, so let's do the most simplest thing. Let's convert 10 grams of NaOH.
The mass of that is 40.
Yes, it is. All right, so y'all can do this in your head. 10 over 4, I'm sorry, 10 over 40, or basically 1 over 4 is what? 0.25. Just move the decimal. Which way? To the left. 1, 2, 3. So 0.225 liters. Moles, liters, divide them. Okay. So 1.1111, which is rounds to 1.11. There's 2 ways you can write the units for this. You can write it with a capital M. You can, I will accept this. Moles per liter. I will accept that too. But it's just a lot easier to write a capital M. Okay. Is that very concentrated, do you think? This. No, it's not that very concentrated. It's a very low number. The higher the number, the more concentrated it is. So if y'all actually played with this in lab, I wouldn't be worried about you burning your hand. So they give you 0.68 moles, and you're supposed to find your volume. Do you know that you're cross-multiplying here?
Yep.
If you look at it like that.
Uh-huh.
You sure? Some of y'all are saying no.
Okay, we'll go
I
on the other
didn't
side.
hear
We
no.
just put a 1 under 2.3.
Okay. When you do that, it's the same. You're basically doing that. You do know that, right?
Yep.
And so you just multiply across straight across?
Yeah.
No.
Well, not straight across. You never do that. You cross multiply.
Okay.
This times this. This times this. What do you get? I didn't understand that, but okay. Okay, so then you divide,
No.
and x equals 0.30. So number 3, how many grams of KCl are needed to make 250 milliliters of a 0.25 molar solution of KCl? Okay, you need to be able to read and know what they give you, all right? So right off the bat, you know they give you this, which is what? That is a volume. So they give you this guy, all right? Then they give you this. What is that? Molarity. All right? You need to find this. However, they say they want it in grams. You can't go straight to grams. You got to go through moles. You know you got to, okay? So, let's plug things in. 0.25 molarity, which is the same thing as what?
That's moles.
Moles over liters.
Liters, man.
Okay, good for you. He wakes up. All right, so they give us 250. Where's that going to go? All right.
First you have to convert it
Say it again.
to liters.
Convert to liters. How do you convert 250 milliliters to liters?
You gonna be that 0.25, man. Be 3 spots, boy.
Y'all going to be doing that a lot this unit. A lot. That'll do me a lot. All right, so we got that guy in there. Now that's in liters.
Lord.
So now we have to figure out this guy. Well, cross multiply. You have fun there? Okay. So cross multiply, what do you get? 0.25 times 0.25.
0.50.
6 what?
2.5.
2.5. All right, so what's 1 mole of KCl?
It's 74.50.
74, whoops. 0.55?
That's what she said.
Grams of KCl. All right, so what this means is this. If I told you to make this solution in the lab, you could do it. Well, yeah, you could. All right, so here's what you got to do. And pay attention because this is what you're going to have to end up doing in the lab part, and I'm not going to tell you after I tell you this. So what does this mean is this. To make this concentration, if I said go in the lab, make this concentration at this volume, you have to figure out how many grams of KCl you're going to need. All right? Well, it's very simple. You set up your ratio like you did, and you solve, and this is how many moles of KCl. Well, you can't measure out in moles. So you go to on the balance, and you take KCl, and you start measuring out on the balance. How many grams of KCl would you need? 4.66. So once you have 4.66 grams, you would take that and put it into 250 milliliters of solution. That would give you the concentration of this. So you just did this part. Do the calculation and find out how much solute you need. So this is how you make the solution. The main thing, and honestly, you don't have to really know all this. The main thing you really got to know is this. What do you put in first? The solid. Put in the solid first. Here's the reason why. If you put in the volume first, and you filled up 250, and then you put in the solid, it's going to overflow. Because doesn't the solid also have a volume? Do solids have volume? Yes, they have a definite volume. They're going to overflow and push the volume overhand. And so therefore, you're not going to end up with 250 milliliters. You're going to end up with over 250. And so that's what we want to avoid doing. So what we want to do is put the solid in first, then fill it up to 250 milliliters. Because remember, molarity is moles of solute over liters of solution. It's not solute per solvent. Again, let me repeat that. It's not solute per solvent. It's solute per solution. Part over whole. So we want our final volume to be 250. So anyway, going through all this, we already did this step. Number 2, use the correct side volumetric flask. Volumetric flask, again, this was many moons ago when we talked about what this guy is. It's a lot like the flask y'all have seen, except these guys only have one volume. What they mean by find the correct size, if the set volume is supposed to be 250 milliliters, okay, then what volumetric flask do you need to go get?
At least 500.
250. They only have one volume. So you're filling up, they're designated to fill up precisely, and I'm talking about 100% accuracy to that line. That's why we only want one volume. We're only going to fill up to that one line. You're like, well, that's just kind of silly. Aren't we going to use this multiple times? Yeah. No, you're not. You want to fill up one stock solution. If you go buy a liter of cola, or a liter of Coke, or something like that, you buy 1 liter. You don't buy 0.99 liters. You want the 1 liter. You want it to be as precise as you possibly can. Add some distilled water to it to make sure that the solute dissolves. Distilled water we'll talk about a little bit later. Just note that is nothing in it. It's just H2O. Yes, it's different from the water you drink from the faucet. Number 4, fill to the line with distilled water. Don't forget to label your container you put it in. If you don't label it, then you don't know what it is. That's like me going mixing things in the chemistry lab and like, no, it's actually me going like into your house and removing all the labels off your cans.
No.
What is this?
That would suck.
That's exactly what it is, what happens when you don't label. Refried beans, or is it corn? No, discuss the rising of what happens followed back. This is the main thing we need to talk about. So just remember this, okay? Put the solid in first, then fill up with liquid, okay? That's really summarizes this whole thing. All right, so here's the thing. Key point, note this, that it is not moles of solute per liters of solvent, okay? It is this, moles of solute per liters of solution. That's part per part. The bottom one here is part per whole. We want to do part per whole. So when you do it in lab and on the Kool-Aid lab, you're going to need to fill it up to put the solid in first and then fill up the volume. If you don't, you're going to get what you see here in a second.
You want to start that slide?
Probably not. So let's say I told you to go make this solution.
Meth.
Okay. This is 1,000 milliliters, which is how many liters?
1.
1 liter. So I said make a liter solution with 25 grams of the copper sulfate. Remember the blue stuff you dehydrated?
Meth.
Yeah, the meth stuff. That's that. So here's the thing. If you filled this up to the line first, okay, so let's say you did put your liquid in first, then your solid. What would happen is this. You put your solid in, what's going to happen to the volume? It's going to rise. This right here is how much volume was displaced, which is not a concentration. So the whole point here is, the lesson is this. Put your solid in first, then fill up the line. Because if you put in your volume first, then put in your solid, it's going to overflow the line. And you're going to have part per part. We don't want part per part. We want part per whole. Okay? So put your solid in first, then do it otherwise. Okay?
Cereal, then milk.
So if I said dissolve 5 grams of nickel chloride, 6-hydrate, which is the whole compound, in enough water to make 250 milliliter solution, I say now calculate the molarity. So instead of you looking up the mass by yourself, I'll go ahead and give it to you. It's right here. Okay? You do know this is the same thing as setting up the crisscross, right? You sure? Okay. Remember the crisscross? Okay. So 5 grams divided by this is going to give you this moles. So why are we putting it in moles?
Because you're trying to get the molarity.
All right, which is?
A mole over liter.
Over liters. So, however, is this in liters?
You got to convert that. We're going to be looking at 0.25 liters.
Okay. And you get this concentration. Is that high or low?
That's a pretty low one.
Now, here's your question. Now that you know what concentration this is going to be, what do you put in first? The liquid or the solid?
I'm putting in that solid.
What is the solid? The 5 grams of NaCl, and don't forget the 6H2O in there, because that's part of the hydrate. So this right here is what you're going to measure out. That's that, and you're going to put it into here. So then you fill it up afterwards. if you put in the liquid first and then put this in after, it's going to overflow. And we don't want overflow. Again, molarity, do keep this in mind. Part over whole, part over total. Okay? If you do it backwards, you're going to mess it up. Note this down here. You see the brackets. You're not going to see this any other time. Okay? You need to know what these brackets mean. It means concentration of. You need to write that down. It's not in the slides. You need to write down brackets mean concentration of. It's going to be important next unit. Okay? So if you see brackets ever in your life, that means concentration of whatever. So anyway, all right, concentration units. The ideal solution, there's that big-nosed guy again, is one of the properties that depend only on the concentration of the solute. We need concentration units to tell us the number of solute particles per solvent. Okay, so sometimes we don't need to know part per whole. Sometimes we need to know part per part. That's where the next formula comes into play. Molarity does not do this. Why does it not do this? Because it is solute over solution. Part per whole. 2 parts make a whole, right? You with me so far? Okay. So we need something that we want to measure the ratio between 2 things. We don't want to measure the part per whole ratio. What if we just want to know part per part? Okay. That's where the next guy comes in, which is molality. Whoops, almost ran to the table. So molality is a lowercase m, and its formula is as follows, which I wrote the shortcut on the board. The molarity of solution is going to end up being the moles of solute per kilograms of solvent. I know. There is a difference. Molarity has an R in it. Molality has an L. That is the only difference in the words. Do you think they could have just made it a little bit different? Well, here's the thing. Most of the time when we make solutions, we're going to use water. Sometimes we might want to use something else like alcohol. All right, so what is the molality of a solution made from 16.1 grams, okay, of chlorine gas in 5,000 grams of H2O. Now, right off the bat, you're like, okay, well, which one is which? Well, again, let's go back to the beginning. Rewind time. Okay, right here, this slide. And I can't believe I nailed it just right. So, solute, the part of a solution that is being dissolved, usually the lesser amount. Which one's lesser?
16 grams.
I kept them both in grams so you can see the ratio. So which one's lesser?
16.1, man.
Solute.
Oh, you.
All right. And I've got usually the greater amount. Which one's greater?
Right there gonna be solvent.
Bam. That's how you're going to know the difference.
Darn straight.
Who's higher is going to be your solvent. The one that's lower is going to be the solute. All right. Now fast forward back. How you got it? Almost got it. I was 1, 2, 3 off. Oh well. Usually I'm pretty good at it. All right, so now we got to figure out the molality. So molality is moles of solute over kilograms of solvent. So guess what we got to do to this guy? Convert to moles. Guess what we got to do to the bottom guy? How do you move the decimal? How many kilograms is this? 5. All right, well we got that one. So we need to find this guy. So 16.1 grams, Cl2. 35.45 times 2. 70 what? 0.9.
9.
There we go. Divide that by that. That's going to be like 2, you're going to have 3 decimal places on this one.
0.227.
227? Not a 0?
227.
I thought there would be another decimal there. All right. Don't push it. That's funny. All right, divide this by that. You're going to end up with another decimal.
0.0454.
Yeah,
0.0. Right?
yes.
Okay. All right, so that's easy to do. Mass, volume, kilograms, whatever, we got it. All right, so the next one is this. How many kilograms of water should you add? So right off the bat, you should know you're finding this guy, the kilograms. All right, should you add to 34.2 grams of sodium chloride to make this molal solution? So 4.5 molal. All right, you cannot plug in the 34.2 here. Why? It's in grams. We got to convert it. All right, so now you cross multiply here, which you're going to end up having 4.5 with x equals 0.485. So you can divide this by both sides.
We have 0.13.
0.13 or 0?
Yes, you get there.
Okay.
You have 4.5.
Because we're dividing it. So up here, you had to crisscross. This will go with that. That will go with this. So you got 4.5 with x. Then you got this on the other side still. So you end up had to divide. Backwards. What's the units for this?
We're gonna be looking at some gram.
Grams.
It is in kilograms.
Oh, could it say how many kilogram?
Yeah. And plus also it's already a kilogram right here. How is this different from 4.5 molar solution of NaCl? This is molal. This is molar. What's the difference?
Well, a letter.
The capitalized pill.
You don't find the kilograms.
This is 4.5 moles per 1 liter. Okay. This over here, which if we actually put it together, going back to the very beginning, 4.5 moles, but per kilogram. So this is part over whole. This is part over part. There is a difference between the two, not just the unit. They do the unit to actually keep you from mixing them up. That's why they do kilograms instead of liters. I know, you're like,
Nah, man.
No, we
they did that to try to help.